One of the drawbacks with an online course is we don't get a chance to build anything that you can actually, honest to God, touch. So some of this logic gate stuff may seem a little bit ethereal. Well, let me just point out that logic gates are very, very real, and we'll talk about some ways that they're actually done today. For example, here's a NAND gate made out of Legos. If you follow the link on the Moodle, you can actually see it in operation. And back in the early 1800s, a guy named Charles Babbage actually built something mechanically that acted like a computer. It was built in base 10, not in base 2, and here's a bunch of it, not all of it. He actually designed something even more powerful, but given the state of the art of building things and machining things at the time, he wasn't able to create it. So a science museum in the UK built this one to his plans a few years ago. In the late 1800s, mechanical computation actually entered the commercial world, where a predecessor of IBM built machines that were used to help count and tabulate the 1890 census. In between the world wars, a lot of activity went into calculating trajectories of large artillery shells, like those fired from ships, to try and figure out where they would land. A mechanical device powered by electricity, again, was used here. This is showing one at MIT built in the middle of the 1930s. Late in the 1930s, though, the breakthrough came. The guy studying at MIT noticed similarities between Boolean algebra and telephone switches. His MIT's master's thesis actually linked the concepts that were invented as Boolean logic back in the 1850s with vacuum tubes used in early telephone switches in the early 1900s to store zeros and ones. And the result was binary digital electronics. And all of the computer technology basically since then relied on this one key insight. A vacuum tube is nothing more than a simple electrical switch. It has 3 terminals. You put a voltage on the top one. You tie the bottom one to ground, and as you'll see in the off position on the left-hand side, the voltage is not connected to ground. So, if I detect the voltage on the top, I will see that voltage as it has no place to go. However, if I place a voltage on the side, on the 3rd terminal, what happens is it enables a path for the voltage to flow through the vacuum tube to ground. When that flows through, you then see no voltage at the top because it's immediately flowing as a current down to ground. An electrical switch. Now remember, we said way back when we were talking about binary logic that zeros could represent the absence of a voltage and 1 represents the presence of a voltage. So here, this electrical switch, which could be embodied in a vacuum tube, changes a 0 to a 1 and changes a 1 to a 0. Oh my goodness. It's a NOT gate. Now let's string 2 of those switches together in series as shown here. If I put a 0 into both sides, no voltage, the switches stay open, and so I see a voltage at the top where I measure it. 0, 0 gives me a voltage out. If I put in voltage on the top one, I'm still going to get voltage out because it's still not connected all the way to ground. Similarly, 0 on the top, voltage on the bottom, it's not connected, I still see a voltage on the top. But if I applied a voltage to both inputs, that completes the circuit and gives me a 0 voltage reading at the top. Interpret the presence of voltage as a 1, the absence of voltage as a 0, and we have a truth table. Yes, indeed, Virginia, we've just built a NAND gate out of 2 vacuum tubes. Remember that NAND logic can create any other set of gates we want. If I want to create a NOT gate, it's pretty easy. All I got to do is take my single input and pump it into both sides of the NAND gate. and the reverse comes out. Now, remember that a AND gate is merely a NOT of a NAND gate. So there's my AND. I'm going to let you figure out how to do the OR, although if you pause this and come back, there'll be a clue for you. Ah, the clue's in algebra. Maybe that's how you could implement the circuit. So, theoretically, I could build any computer using nothing but vacuum tubes. And in fact, the first electronic digital computer, the ENIAC, was built using vacuum tubes. It lived from about 1946 to 1955 in operation. It was actually built on a crash project during World War II, first to try and fire artillery shells, and then second to support computations for the development of the atomic bomb. And it did an incredible number of additions per second, over 1,000 additions per second, which is probably a lot faster than you can do them, even in binary. However, vacuum tubes have a significant problem. They drink lots of power, and they burn out very frequently. If you have lots and lots and lots and lots of vacuum tubes, as you can see in that picture, the chances that at any point in time one's going to burn out are pretty high. So the computer didn't stay up for very long. What really got things going was the transistor. Developed by a number of people, although William Shockley took all the credit, at Bell Labs in the late 1950s and early 1960s, it replaced that function of the vacuum tube with something that worked, frankly, through quantum physics. And it was much, much more reliable, and obviously much cheaper to operate, took less power, and was a lot smaller. That led to the second generation of computer technology, where, as you see, we're now up to about 500,000 adds a second. Now, we weren't yet using transistors for memory, because transistors have this problem that they don't remember anything if you turn the power off. Just like a lot of memory today, it's built out of transistors, does not remember anything after you turn the power off. So instead, magnetic core memory was used instead. And they literally ran physical wires at right angles through magnetic cores and either magnetized them or demagnetized them to store a 0 or a 1. When you hear programmers today refer to core memory or a core dump, it's actually thinking back to that second generation of computers in the late 1960s and early 70s using core memory. The next major breakthrough came when we realized that we could put multiple transistors, and in fact multiple logic gates, into the same package. We could integrate them all into a single circuit, an integrated circuit. And even today you can still buy a quad 2-input NAND buffered B-series gate from Fairchild Semiconductor for about 50 cents a piece. Integrated circuits led to what people generally refer to as the third generation of computers, where we now had to start measuring instructions per second in the millions. 10 million instructions per second now, up from that initial 1,000 just 20 years before. I'm not sure there really is a fourth generation, because it's just more of the same stuff, done really, really fast and really, really small, but you can see we're now up into the billions of instructions per second on the latest Alienware laptop from Dell. Moore's law is the shorthand for representing this incredible increase in processing power based on transistors. You see, way back in the initial days, 1,000 transistors per integrated circuit, now up to 2 million and above for the latest complex chips. And perhaps a more interesting way of looking at this is calculations we can do per second per $1,000. And you can see way back in the 1900s, computations were extremely expensive. And now, 14 orders of magnitude later, they're incredibly cheap. When will it end? Well, that's a topic for our discussion board. Some people say soon, some people say never.